Welcome to a world that turns quietly beneath the surface of everything you see. Gears, simple in appearance, yet complex in purpose. They make machines move, clocks keep time, and vehicles roam vast distances. Without them, our world would stop. The wheels of industry, the heartbeat of technology, the silent power behind every mechanical motion. This is the story of gears. Take a moment, feel the weight of that thought. Every spinning object, every rotating part depends on gears working in harmony. The unseen dance of teeth meshing together, turning force into motion with remarkable precision. This is not just engineering, it is magic made real through science and design. Before we journey deeper, I want to connect with you, wherever you are, whether in a bustling city or a quiet town. Leave a comment telling me where you are watching from and what time it is there. Now settle back, let your mind relax, because what unfolds next is an exploration, deliberate, slow, and full of wonder. What exactly is a gear? At its simplest, a gear is a wheel with teeth cut around its edge. These teeth fit precisely with the teeth of another wheel. When one turns, it causes the other to turn. This transfer of motion and power is fundamental to machines. But what seems simple on the surface hides a rich world of shapes, sizes, and uses. The teeth are the key. Their shape, size, and arrangement determine how smoothly and efficiently the gear moves. Each gear revolves around an axis. The invisible line where gears actually meet is called the pitch circle, the true point of contact. The size of the teeth is measured by something called the module, which is essential to matching gears perfectly. The thickness of the gear across its face, known as face width, influences strength and durability. Imagine a clock. The ticking of the second hand is no accident. It's driven by gears, each tooth engaging the next with perfect timing. This interplay controls speed, direction, and power. The precision in that tiny mechanism is immense. There are many types of gears, each designed for a unique purpose. Spur gears have straight teeth and are the most common. Helical gears lean their teeth at an angle, resulting in smoother, quieter operation. Bevel gears change the direction of rotation, often at right angles, essential in car differentials and machinery. Worm gears resemble screws and are used where high torque and slow speeds are necessary. These types only scratch the surface. Underneath lies a diverse universe of gear forms, materials, and applications. But for now, imagine the countless machines around you, all reliant on these humble wheels. Gears are not just mechanical components. They embody human ingenuity, the art of controlling motion with exactness and reliability. They connect forces, transform energy, and enable the impossible. The story of gears is as old as civilization, and as enduring as progress itself. Their secrets will unfold gently, a step at a time, revealing a world where science meets art in every turn. And so the gears begin to turn, slowly, purposefully, drawing you into their timeless rhythm. Gears have a history that stretches back thousands of years, reaching deep into the dawn of human ingenuity. Their story begins long before factories and automobiles, rooted in the quest to harness and control motion. Ancient civilizations first glimpsed the power of rotating wheels and teeth, and from those simple beginnings, a world of mechanical marvels has grown. The earliest known gears appeared around the 3rd century BCE, the Antikythera mechanism, a remarkable ancient Greek device used a complex system of gears to predict astronomical events and calendar cycles. This early example reveals that gears were not just practical tools but instruments of knowledge, unlocking secrets of the cosmos through precise movements. It was an extraordinary achievement in an era without modern tools or machines. The gears in the Antikythera mechanism turned slowly, elegantly, revealing how early minds could design systems of incredible precision. From Greece, the use of gears spread across time and geography, fueling innovations in water mills, grinders, and clocks. In medieval Europe, the development of mechanical clocks became a focal point for gear design. These clocks introduced the world to the concept of gear trains, multiple gears working in harmony to create measured continuous motion. The ticking sound you hear in an old clock is the breath of countless gears engaging and releasing in a rhythmic cadence. Meanwhile, in the East, civilizations in China and the Islamic world advanced gear technology to power astronomical instruments, automata, and even early gearing systems in water-raising devices. The evolution of gears was a global story, shaped by many cultures, each adding a new chapter to the unfolding narrative of motion control. By the Industrial Revolution, gears emerged as the heart of a mechanical age. Steam engines, textile machines, and early automobiles all relied on gears to regulate speed and distribute power. The precision manufacturing of gears became an art and science, every tooth cut to exact dimensions to ensure efficiency and longevity. The growth of factories depended on quiet, reliable gears turning day and night, transferring energy and motion. The design principles from those early machines still guide gear engineers today. Understanding tooth profile, pitch, and load distribution is essential. Over time, gears have been made from wood, brass, steel, and now advanced alloys and composite materials. Advances in manufacturing, such as CNC machining and 3D printing, allow even greater precision and complexity. Yet the fundamental physics remain unchanged. Gears must mesh smoothly, transferring torque without slipping or grinding. The angle and shape of the teeth, the materials used, and the alignment all contribute to the gear's performance and lifespan. This story of gears is one of continuous improvement, of human creativity propelled by a desire to master motion. It is a tale where every invention builds on the last, creating a legacy of innovation that powers our world today. So, as we reflect on this long history, consider the unbroken chain of ideas and hands that shaped these turning wheels. Each gear tells a story of cultures, epochs, and breakthroughs, a story that continues as you watch and listen. Every rotation is a connection to this ancient craft, a link between past ingenuity and future possibilities. The past whispers through the teeth of every gear, inviting us to explore further, to discover not only how gears work, but why they matter, why they continue to inspire engineers, artisans, and dreamers alike. And so, as the gears of time keep turning, we move deeper into their world, ready to unlock their types, principles, and the endless variety of ways they transform our lives. The rhythm of discovery continues, steady and sure, turning slowly, but never stopping. Gears are astonishing in their variety and design, each type tailored to solve a unique engineering challenge. To understand gears deeply, it is essential to explore their main classifications and how their shapes and arrangements influence motion. Every gear type represents a different approach to transmitting power, whether speed, torque, or direction, and mastering these distinctions unlocks the full potential of mechanical design. The most familiar gear is the spur gear. It is often the first image that comes to mind. A simple wheel with straight teeth aligned parallel to its axis of rotation. Spur gears are fundamental for transmitting motion between parallel shafts. Their geometry is straightforward, making them easy to manufacture and highly efficient in transferring power. However, the abrupt engagement of tooth profiles causes noise and stress, especially at high speeds. Despite these limitations, spur gears remain indispensable in countless mechanical systems such as clocks, washing machines, and conveyors. Their simplicity hides the reliability that underpins so many everyday machines. Moving beyond the spur gear, the helical gear introduces a more refined design. Unlike spur gears, helical gears feature teeth cut at an angle to the axis. This angled cut results in gradual engagement of teeth, which dramatically reduces noise and vibration while improving load distribution across the tooth surface. Helical gears can transmit power between parallel shafts like spur gears, but their smoother operation makes them ideal for high-speed, high-load applications, including automotive transmissions and industrial machinery. Moreover, they can also be employed with shafts at right angles, sometimes creating a subtle crossover in function with bevel gears. Bevel gears, in turn, are specialists in changing the axis of rotation. Typically configured with a conical shape, bevel gears transmit power between shafts that intersect, usually at a 90-degree angle. Picture the differential gears in a car's axle. Bevel gears seamlessly transfer torque from the drive shaft to the wheels. These gears demand meticulous alignment and manufacturing precision to ensure smooth operation, because the contact surfaces are more complex than those of spur or helical gears. Variations like spiral bevel gears bring an added element of smoothness by utilizing curved teeth, combining the benefits of helical and bevel designs. Next, consider the worm gear, a truly unique member of the gear family. In this arrangement, a screw-like worm meshes with a gear similar to a spur gear, offering a significant mechanical advantage by substantially reducing speed while increasing torque. Worm gears are inherently self-locking, meaning they prevent motion from reversing back through the gear train, which is invaluable in lifting applications such as elevators and hoists. Despite their high torque output, worm gears are less efficient due to sliding contact between the worm and the gear, causing heat and wear. Beyond these common examples lie specialized gears, such as rack and pinion systems, which convert rotary motion into linear motion. Think of steering mechanisms in vehicles. Planetary gears, which pack gear trains into compact high-torque arrangements used in automatic transmissions and robotics. And hypoid gears, a variant of bevel gears used in car differentials for even smoother power transmission at reduced noise levels. Each gear type embodies a carefully calibrated balance of shape, function, and material to meet exacting needs. Understanding these differences is fundamental to designing or repairing machinery that performs reliably and efficiently. But why do gears look the way they do? The answer lies in the geometry of their teeth. Two gear teeth must fit together precisely. The involute profile, a curve generated by unwinding a string from a circle, has become the standard shape for modern gear teeth because it guarantees constant velocity ratio and smooth engagement. This geometry ensures that the speed ratio between gears remains steady even if their center distance varies slightly, reducing stress and wear. Every angle, every curve, and every measurement in gear design serves the dual purpose of efficiency and longevity. Material choice, lubrication, and manufacturing accuracy all interplay with the gear's geometry to produce motion that is both reliable and silent. As we move forward, these principles will repeatedly surface, illustrating that gear design is as much an art as it is a science. In this vast and intricate landscape of gears, each type reveals a different facet of a world designed to control motion with excellence. The gentle thrum of a helical gear, the decisive turn of a bevel gear, or the stubborn grip of a worm gear. All these contribute to the complex symphony that powers modern engineering. Watch closely as we begin to peel back the layers of these mechanical wonders. Each gear's design is a story of problem solving, a tale of form meeting function, and a legacy of human curiosity spun into metal. The gears are in motion. The journey continues, slow and deliberate, uncovering the secrets concealed within these turning machines. Gears do not exist in isolation. They function as parts of systems, each with a specific role tailored to its environment and purpose. Understanding the principles behind how gears transfer and transform motion opens the door to grasping the very core of mechanical engineering. These principles guide the design choices engineers make, ensuring efficiency, durability, and safety in everything from small gadgets to massive industrial machines. One of the most fundamental concepts is torque, the twisting force that causes rotation. Gears can increase or decrease torque depending on their size and arrangement. For example, a small driver gear turning a larger driven gear will increase torque at the expense of speed, whereas the reverse increases speed but reduces torque. This interplay between speed and force is manipulated in countless machines, enabling engines to accelerate vehicles smoothly, or cranes to lift enormous loads with precision. Closely connected to torque is the concept of the gear ratio. This ratio compares the number of teeth between the driving gear and the driven gear, dictating how many turns one gear makes relative to the other. For instance, a gear ratio of 4.1 means the driver gear must turn 4 times to make the driven gear complete one rotation. This simple mathematical relationship becomes a powerful tool, allowing engineers to fine-tune machines for specific performance requirements, from the fastest sports car to the slowest, most powerful winch. But the transmission of power through gears is not merely about force and speed. It is also about the direction of motion. By carefully arranging gears, motion can be redirected, reversed, or split. A pair of meshed spur gears will rotate in opposite directions, while certain bevel gear setups allow shafts to turn at right angles, facilitating complex mechanical movements in compact spaces. In more sophisticated configurations, planetary gear systems distribute power among multiple rotating components simultaneously, creating compact assemblies capable of huge torque outputs and smooth variable speed control. These principles extend beyond simple gear pairs into entire gear trains, chains of interconnected gears working together. The design of a gear train involves careful consideration of each gear's size, tooth count, and mounting to achieve the desired output motion and torque. Whether in a clock's delicate escapement mechanism or an industrial gearbox powering conveyor belts, the harmony of gear trains ensures steady, controlled movement. Yet, as much as gears are designed for motion, engineers must also navigate the challenges of wear and durability. Every mesh is a point of contact where friction, stress, and heat converge. Hence, material selection is critical. Early gears were crafted from wood or brass, sufficient for low-stress applications. Today, advanced steel alloys, often heat-treated for hardness, dominate to endure enormous forces without deforming. Alongside material science, lubrication plays a pivotal role. It forms a thin barrier allowing teeth to glide over one another smoothly, dissipating heat and reducing wear. Another crucial consideration is the efficiency of gear systems. Perfect gears would transfer 100% of energy without loss, but the reality is different. Friction, backlash, the slight gap between mating teeth, and imperfect alignment reduce efficiency. In high-performance machinery, minimizing these losses matters enormously, improving fuel economy in vehicles, reducing energy use in factories, and extending the lifespan of equipment. Engineers employ tight manufacturing tolerances, precision machining, and advanced coatings to push efficiency ever closer to perfection. Noise is an often overlooked but omnipresent consequence of gears in motion. The abrupt engagement of gear teeth, especially in spur gears, creates vibrations and sound. Engineering quieter gear systems has inspired innovations like helical teeth, which engage gradually, and careful balancing of rotating parts. In sound-sensitive environments, such as electric vehicles or residential machinery, reducing gear noise transforms the user experience. The physical geometry of gear teeth further influences performance. The involute profile mentioned earlier ensures consistent speed transmission. But the complexity does not end there. Tooth size, pressure angle, the angle at which teeth contact, and root shape all influence strength and how forces travel through the gear. Engineers use sophisticated computer models and testing to optimize these features for each application, ensuring no tooth bears excessive load that could lead to failure. With all these factors, torque, speed, direction, material, lubrication, efficiency, noise, and detailed geometry, gears present a formidable challenge and opportunity. They are the embodiment of precision engineering, where physics, material science, and creativity converge. In motion, gears reveal the elegance of mechanical reasoning. Each turn is a demonstration of centuries of accumulated knowledge, blended with innovation to solve new problems. Whether in the precise timing of a luxury watch or the massive torque conversion of a wind turbine gearbox, gears operate quietly, persistently, and reliably. So as the wheels continue to turn, consider that every tooth tells a story of design choices, sacrifices, and mastery over motion. The hum you hear is a symphony of forces balanced perfectly. The complex dance of teeth meshes the tangible and the theoretical, the practical and the beautiful. And here, at the crossroads of engineering and craftsmanship, our path winds deeper. The principles we have touched upon now form the foundation for exploring how gears are made, how they are measured, and how engineers ensure they perform flawlessly over countless cycles. The journey through the world of gears continues. Each revelation turns the wheel of understanding further, inviting you to listen closely to the subtle language of metal in motion. The creation of gears is a meticulous blend of art and science, where precision engineering meets advanced manufacturing techniques. Every gear begins as raw material, often steel or specialized alloys, chosen carefully for strength, toughness, and resistance to wear. But the journey from solid metal to a perfectly meshing gear involves multiple steps, each requiring exacting control and expertise. First comes the selection and preparation of the material. Engineers assess the required strength and operating conditions to decide on the best alloy. These materials may undergo treatments such as carburizing or nitriding, processes that harden the gear's surface while retaining a tougher, more ductile core. This process ensures the teeth withstand the constant contact stresses and resist fatigue for years of reliable operation. Once the right material is set, the next phase is shaping the gear blank. Large blocks of metal are cut or forged into round discs or cylinders roughly matching the final gear's size. Forging imparts strength to the metal fibers by aligning them in patterns that support load bearing, while casting is used for larger or more complex gear bodies. After rough shaping, the blank is machined to its precise dimensions before the teeth are cut. Cutting the gear teeth is one of the most critical operations. Traditional methods include hobbing, shaping, and broaching. Hobbing uses a specialized cutting tool called a hob, which rotates continuously as it cuts the gear teeth, a fast, efficient way to generate precise, standardized teeth. Shaping involves a cutter moving back and forth, carving one tooth at a time with unmatched accuracy. For internal gears, broaching removes excess material by pulling or pushing a toothed tool through the gear blank. Modern industry also employs gear grinding, a high-precision finishing step. Grinding polishes the teeth to exact smoothness and shape, removing tiny imperfections that could cause noise or premature wear. This process allows gears to meet incredibly tight tolerances, as little as a few microns, essential in high-speed or sensitive mechanical systems. Alongside mechanical cutting, advancements in computer-aided design and manufacturing CAD/CAM have revolutionized gear production. Digital models guide tooling and control every motion during cutting, ensuring every tooth conforms to the ideal involute profile and precise dimensions. These technologies shorten production cycles and increase consistency, making it possible to manufacture complex gears for aerospace, robotics, or automotive applications with unparalleled quality. Even more recently, additive manufacturing, or 3D printing, has begun to play a role in gear prototyping and low-volume production. Though not yet common for high-stress gears, this technology allows rapid iteration of complex geometries that traditional methods struggle to produce, opening new avenues for innovation in gear design. Beyond shaping, heat treatment remains a cornerstone of gear manufacturing. This stage involves heating treated gear blanks to specific temperatures and then cooling them rapidly or slowly, altering internal structures to increase hardness and durability. The process is tailored precisely depending on the gear's intended application, balancing toughness with resistance to wear and fatigue. After shaping and heat treatment, gears undergo thorough quality control. Inspectors measure tooth dimensions, profile accuracy, pitch, and surface finish using tools ranging from micrometers to sophisticated coordinate measuring machines and even laser scanners. Detailed inspection ensures that the gears will mesh smoothly, maintain correct alignment, and endure operational stresses without failure. The manufacturing process does not end here. Gears may receive additional surface treatments, like coatings or lubricants to resist corrosion, reduce friction, or enhance wear resistance. The choice of lubricant itself is a crucial partner in gear longevity. Frequently synthetic oils designed to maintain viscosity and protective properties under extreme heat and pressure. All of these steps, from material selection to final inspection, underscore the precision and dedication involved in making gears. The smallest error in tooth shape, surface finish, or material treatment can cause inefficiency, noise, or catastrophic failure. That is why skilled engineers and machinists take great care in every stage. As you imagine a gear rolling into place inside a gearbox or machine, consider the incredible journey it has taken. From raw metal shaped by fire and steel to a masterfully crafted tooth designed to mesh perfectly with its partner, every gear embodies the culmination of science, craftsmanship, and centuries of accumulated knowledge. Through this intricate process, simple wheels become the silent workhorses of machinery. Their perfect interaction drives engines, rotates turbines, controls robotic arms, and turns the world's clocks. The manufacturing story of gears reveals the passion and precision behind every revolution, every rotation, every turn of the mechanical world. With this understanding of how gears are made, we gain deeper appreciation for the complexity hidden behind what might seem like an ordinary part. In the quiet moments when gears mesh and hum, the story of their creation comes alive, testament to human skill, patience, and innovation. So as the gears keep turning ever onward, remember that behind their smooth motion lies a saga of material science, cutting-edge manufacturing, and unwavering precision. The exploration of gears continues, revealing more layers of their fascinating existence. Gears do not simply exist as isolated mechanical components. They live within complex systems that depend on precision alignment, tolerances, and careful assembly to function correctly over time. The way gears are mounted and balanced within machines significantly affects their performance, longevity, and the overall efficiency of the mechanical system. This sets the stage for understanding how engineers ensure that gears mesh perfectly, transferring power smoothly with minimal loss or wear. Central to this is the concept of gear alignment. For two gears to engage properly, their axes must maintain precise positioning relative to each other. Any deviation, known as misalignment, can cause uneven tooth contact, increased friction, noise, or even accelerated wear and eventual failure. Aligning gears is a delicate process involving careful positioning of shafts, bearings, and housing components, often facilitated by precision machining and alignment tools. Closely related is the notion of backlash, the small intentional gap between mating gear teeth. Backlash provides room for lubrication, thermal expansion, and manufacturing tolerances, preventing the gears from binding or seizing. However, too much backlash makes the gears play, resulting in loss of precision, increased noise, and reduced efficiency. Engineers must strike a balance, often aiming for minimal backlash to ensure accuracy while preserving enough clearance to protect the gears. These factors become even more critical as speed and load increase. High-speed trains, aircraft transmissions, or precision robotic arms demand gears to operate quietly, smoothly, and with extreme accuracy, often within microns of tolerance. In such contexts, advanced testing techniques, including vibration analysis and thermal imaging, are employed to monitor gear performance and predict maintenance needs before problems arise. Another vital aspect is lubrication. Gears operating under heavy loads or high speeds generate significant heat and friction at the teeth contact zones. Without proper lubrication, friction leads to rapid wear, surface scoring, or even catastrophic failure. Lubricants carefully chosen oils or greases form a thin film separating the gear teeth, reducing friction and removing heat from the contact surfaces. Some specialized gearboxes use oil baths or circulating oil systems, while others rely on grease applied intermittently. The correct lubricant depends on factors like gear speed, load, temperature, and environment. Together with alignment and lubrication, bearing support plays a critical role in ensuring the correct positioning and smooth rotation of shafts on which gears are mounted. Bearings absorb side loads, radial loads, and axial forces, maintaining the shaft's stability. High-quality bearings reduce vibration and noise, and extend the operating life of the entire gear assembly. Without adequate bearing support, even perfectly cut gears would suffer from wobbling shafts and premature wear. Beyond these practical concerns lie the standards and classifications that help engineers design and communicate about gears with precision. Organizations like AGMA, American Gear Manufacturers Association, and ISO, International Organization for Standardization, have developed rigorous standards covering gear quality, measurement, and testing. These standards ensure that gears produced in different locations or by different manufacturers maintain compatibility and reliability worldwide. Gear inspection uses specialized equipment to measure deviations in tooth profile, pitch, runout, and surface finish. Techniques such as coordinate measuring machines, CMM, profilometers, and laser scanners provide digital precision far beyond the limits of human eyesight. This data guides engineers in adjusting manufacturing processes or assembly parameters to achieve optimal gear mesh quality. In complex machinery, engineers also contend with thermal effects. As gears operate, friction generates heat, causing materials to expand. This thermal expansion can change gear tooth clearances, affecting backlash and alignment. Systems are often designed to accommodate these temperature-driven dimensional changes, using materials with low thermal expansion coefficients or adjustable components to maintain gear mesh integrity. Understanding these practical factors transforms our view of gears from static objects into active participants in a carefully balanced system. The laws of physics, material science, and engineering all converge in this dance of rotation, engagement, and force transmission. At this intersection, knowledge and craftsmanship meet, enabling gears to serve reliably under a vast range of conditions. From the delicate mechanisms of wristwatches to the towering drives of industrial cranes, it is where precision engineering becomes art, ensuring that every gear not only turns but does so with grace, longevity, and purpose. So as these turning wheels propel machinery, convey energy, and orchestrate motion, Remember the invisible efforts that maintain their harmony. The alignment, the lubrication, the support, and the unseen calculations that perfect each engagement are all vital to the gear's silent symphony. The dance of the teeth goes on, steady and sure, drawing us further into the intricate world of mechanical motion. And as these principles weave into every system, the story of gears unfolds with ever more depth, complexity, and fascination. Gears find their place in an astonishingly broad spectrum of applications, each harnessing the unique properties of gear interaction to solve specific engineering challenges. Their versatility spans from the tiniest wristwatch to the mightiest industrial machines, emphasizing that understanding gear applications is essential for appreciating how fundamental these components are to modern technology. Consider the humble clock. Here, gears manifest the invisible power of precise timekeeping. Through a carefully arranged sequence of wheels, gears regulate the steady movement of second, minute, and hour hands. Small spur gears mesh to divide rotation into accurate increments, ensuring that time itself becomes measurable and reliable. The peace of mind we find in checking a clock stems from the silent, consistent work of those spinning teeth beneath the face. Expand your vision to the automobile, a marvel of integrated gear systems. The engine's rotational power is transferred through a complex transmission gearbox, where multiple gears, spurs, helicals, and sometimes planetary work together to modulate speed and torque. This allows a vehicle to accelerate, maintain speed efficiently, and handle varying terrains. Differentials utilize bevel or hypoid gears to split power between wheels, while enabling differences in wheel speed during turns. Without these intricately meshing gears, the modern car as we know it would be impossible. Going further into industry, manufacturing equipment relies heavily on gears to automate repetitive processes. Conveyor belts, robotic arms, milling machines, and presses integrate various gear types to ensure precision, repeatability, and power transmission. Helical and worm gears often appear here, selected for their quiet operation and ability to transmit high torque at low speeds. The very factories that produce goods essential to daily life are pulsing with the energy of countless gear assemblies, invisible but vital. The world of aerospace challenges gears with extreme demands, lightweight designs paired with enormous strength and reliability. Aircraft engines incorporate sophisticated planetary gearboxes, allowing turbines to spin at very high speeds while delivering manageable output speeds for propellers or rotors. Precision and robustness are crucial because failure is not an option in flight. Materials used in aerospace gears include advanced alloys and composites engineered to resist temperature extremes and fatigue. In renewable energy, gears transform natural forces into usable power. Wind turbines utilize large planetary gearboxes to convert slow turnings of massive blades into higher speed rotation, suitable for electrical generators. These systems must endure variable loads, harsh environmental conditions, and operate quietly for decades. The subtle precision of their gear trains drives the sustainability of future power generation. Beyond heavy machinery, gears also play critical roles in consumer electronics and medical devices. In cameras, gears adjust lens focus smoothly and accurately. In printers, they drive paper feed mechanisms. In precise surgical robots, tiny gears coordinate movements with micron-level accuracy. These applications showcase the range of scale at which gears operate, from vast to miniature, all sharing common principles of mechanical engagement. Even in daily objects like bicycles, gears provide riders with control over speed and effort. A derailleur system shifts a chain across different sprockets, effectively changing gear ratios to handle hills or flat roads. This manual use of gears embodies a simple yet profound method of mastering motion and force in a living, moving system. Every gear application reveals layers of complexity and design challenges. Engineers must consider load capacity, desired speed ratios, noise restrictions, environmental factors, and space constraints, all while ensuring safety and maintenance ease. This complexity anchors gears as both fundamental elements and pinnacle achievements of mechanical design. Yet despite the variation in size, material, and configuration, all gear applications share a unifying theme. They translate motion, power, and force with incredible precision. Whether accelerating a car, moving an industrial robot, or telling time, gears ensure that mechanical energy flows exactly where and how it is needed. The seemingly simple idea of teeth meshing is in reality a gateway to endless innovation. Each application is a solution, and every solution pushes gear technology further from the early wooden gears of history to the ultra-high precision systems powering tomorrow's machines. As this voyage unfolds, the story of gears deepens, revealing the profound impact of these mechanical wonders on our lives. The rhythm of industry, transportation, energy, and technology beats to the steady pulse of engaging teeth, forever turning and transforming our world. In the continuing dance of engineering, gears remain one of the most enduring and versatile movements, the silent force making the impossible possible. At the heart of every gear's performance lies the principle of mechanical advantage, the ability to amplify force, change speed, or alter direction of motion. This concept, fundamental to all machines, is perfectly embodied in gear systems. Understanding how gears leverage mechanical advantage unlocks the door to designing efficient, powerful, and precise machinery. Imagine the relationship between two meshing gears as a conversation where force and motion are exchanged. When a smaller gear drives a larger gear, the output force or torque increases, while the rotational speed decreases. This trade-off allows machines to lift heavy loads with relative ease or move parts slowly but powerfully. Conversely, driving a smaller gear with a larger one increases rotational speed but reduces torque, enabling faster operations for tasks that require high-speed motion rather than brute force. This balance between torque and speed is captured by the gear ratio, calculated by dividing the number of teeth on the driven gear by the number of teeth on the driver gear. For instance, if the driver has 20 teeth and the driven has 60, the gear ratio is 3.1. The driven gear will rotate once for every 3 turns of the driver, producing 3 times the torque but at 1/3 the speed. This precise control of movement empowers engineers to tailor machinery performance to exact requirements. In complex systems, multiple gears combine to create compounded gear ratios, called gear trains. These arrangements can fine-tune output speed and torque across several stages, distributing loads and optimizing efficiency. For example, a 3-stage gear train multiplies the gear ratios at each step, enabling dramatic changes from input to output rotation. Planetary gear trains represent an elegant subtype, where a central sun gear interacts with multiple planet gears around a ring gear, producing compact, high-torque assemblies. Such configurations are favored in automatic transmissions and robotics due to their smooth operation and compact size. Beyond simple ratio changes, gears also alter the direction of rotation and axis orientation. When 2 spur gears mesh, their shafts rotate in opposite directions, a straightforward reversal of movement. Bevel gears allow the transmission of power between intersecting shafts commonly at right angles, changing the axis and direction simultaneously. Worm gears, where a helical worm engages with a worm wheel, transform rotary motion into linear or very slow turning motions, typically with a high reduction ratio and self-locking capabilities. These directional shifts prove essential in machinery design, whether redirecting rotary force within a gearbox, or translating rotation to linear movement in rack and pinion mechanisms. The ability to control direction extends the usefulness of gears across countless applications. Mechanical advantage also extends to load distribution. Helical and spiral bevel gears, with their angled and curved teeth, allow multiple teeth to be in contact simultaneously during rotation. This distributes force more evenly across the teeth, reducing wear and increasing the gear's ability to handle higher loads quietly and efficiently. In contrast, spur gears engage teeth one at a time, causing greater impact stress and noise, especially at high speeds. The material quality and heat treatment of gears further enhance their capacity to transmit mechanical advantage safely. High-strength alloys and surface hardening processes increase resistance to fatigue, surface pitting, and deformation, ensuring reliability even under extreme loads. Lubrication complements these material properties, reducing friction and dissipating heat generated by mechanical interactions, preserving the gear's integrity and performance. When gears mesh with precision, the result is an elegant synergy of physics and engineering, a controlled transfer of energy that harnesses mechanical advantage to perform work efficiently and predictably. Machines can lift colossal weights, accelerate vehicles, and execute delicate maneuvers with a dependability rooted in these fundamental principles. This mastery of motion enables technology to move beyond human muscle alone. Gears convert raw input into versatile output, shaping the mechanical landscape of everything from handheld tools to massive industrial infrastructure. The mechanical advantage embedded in gear pairs defines the boundary between possibility and impossibility in machine design. As engineers continue to innovate, new materials, lubrication methods, and manufacturing techniques enhance the mechanical advantage of gears even further. High-performance vehicles, renewable energy systems, aerospace engines, and smart robotics depend heavily on these refined gear systems to push the limits of efficiency and power density. The story of gears is ultimately a story about the power of transformation, turning force into motion, motion into work, and work into progress. At every turn, the principles of mechanical advantage reveal the immense potential hidden within these seemingly simple wheels. So as we observe the smooth rotation of gears in machines, remember that behind every tooth lies centuries of understanding how to amplify force and control speed. This understanding continues to shape the machinery that propels civilization forward. Turn by turn, tooth by tooth. Gears do not act alone. They are part of intricate mechanical systems, where forces and motions interplay in complex and fascinating ways. To grasp the full potential of gears, it is critical to delve into the physics governing their interaction, how forces transfer, how stresses develop in the teeth, and how engineers manage these factors to prevent failure and ensure longevity. When two gear teeth engage, contact occurs along a small surface area. This contact surface bears enormous pressure as rotational forces push the teeth against each other to transfer torque. This pressure, known as contact stress, must be carefully managed because it deforms the tooth surfaces microscopically. If the stress exceeds the material strength, it causes surface fatigue, pitting, and eventually gear tooth failure. Therefore, understanding contact stress is vital to gear design and material selection. The distribution of stress within a gear tooth is not uniform. The highest stresses occur at the tooth root, the base where the tooth connects to the gear body. This area experiences bending forces as torque forces push the tooth against its mate. Excessive bending stress can initiate cracks, leading to tooth breakage. To mitigate this, engineers design tooth profiles with smooth fillets at the root and avoid sharp corners that concentrate stress. Heat treatments and surface hardening also strengthen the tooth root against fatigue. Another form of stress is surface wear, caused by the continuous sliding motion between gear teeth. Sliding friction leads to material loss or surface scoring, which degrades gear performance over time. Lubrication is fundamental here, forming a protective film between teeth to minimize metal-to-metal contact. The choice of lubricant, its viscosity, and application method directly impact wear rates and gear life. The dynamic nature of gears introduces additional considerations. At high speeds, factors such as inertial forces, vibrations, and centrifugal effects can impose fluctuating loads on gear teeth. These dynamic loads may exceed static load predictions and cause unexpected stresses or noise. Engineers combat these challenges through careful balancing, damping, and precise manufacturing tolerances to reduce vibration excitation. Gear designers use standardized calculations to estimate load capacity, the maximum load a gear tooth can safely carry. These calculations incorporate factors like material strength, tooth geometry, surface finish, operating environment, and safety margins. Using formulas developed through decades of research and testing, engineers predict how gears will perform under various loads and conditions before manufacturing. Modern gear analysis often employs finite element methods. FEM advanced computer simulations that model detailed stress patterns within teeth under load. FEM allows identification of weak points, optimization of tooth shapes, and evaluation of potential failure modes, without costly physical prototypes. These simulations have revolutionized gear design, enabling engineers to push performance limits safely. Temperatures within gearboxes influence material properties and lubrication effectiveness. Excessive heat reduces lubricant viscosity, increasing friction and wear, and may soften gear surfaces, lowering strength. To mitigate heat buildup, engineers design gearboxes with efficient cooling systems, select high-temperature resistant lubricants, and optimize gear tooth contact to reduce frictional losses. Manufacturers subject gears to rigorous testing to verify their ability to withstand stresses. Tests include endurance runs under simulated loads, noise and vibration monitoring, and failure analysis. Through this cycle of design, testing, and refinement, gears evolve to meet the demanding requirements of modern machines. Additionally, surface engineering plays an essential role in enhancing stress resistance. Coatings such as nitrides or diamond-like carbon films reduce friction and improve hardness, extending gear life in extreme environments. Surface textures can also be engineered to retain lubricant films better, optimizing wear resistance. Understanding gear tooth stresses and forces is not merely an academic exercise. It is the gateway to engineering systems that last. Every tooth must resist fatigue over countless cycles, endure harsh conditions, and maintain perfect mesh to transmit power flawlessly. The sciences of contact mechanics, materials engineering, and lubrication converge here to safeguard the gears that sustain the rhythm of machines worldwide. By appreciating the forces at play within gear interactions, we gain insight into why gear design is so critical, how failure is prevented, and what enables these simple wheels to drive sophisticated technology for months or decades without interruption. These hidden stresses and the engineering responses to them reveal the true artistry behind gear systems, a blend of physics, material science, and precision craftsmanship. It is this mastery that allows gears to quietly carry enormous loads and perform their vital role reliably. As metal teeth engage and spin, the dance of forces continues, each rotation a testament to the strength and resilience crafted into their design. The story of gears is as much about managing invisible forces as about movement, and each tooth carries this legacy forward in every turn. Beyond the mechanical and physical intricacies of gear function lies the fascinating world of material science, a critical domain that shapes the durability, strength, and performance of gears in every application. The choice of material and its treatment affects how gears endure the relentless demands of motion, load, and environmental exposure. defining their ability to operate reliably over time. Historically, early gears were crafted from wood, bronze, or brass, materials that were adequate for low-stress, low-speed applications. Wood was easy to shape but limited in strength and susceptible to wear and water damage. Bronze and brass offered better durability and resistance to corrosion, but were still limited in load capacity. With the advent of the Industrial Revolution and the rise of high-power machinery, these materials gave way to hardened steels, heralding a new era in gear manufacturing. Steel remains the dominant gear material, prized for its unparalleled combination of strength, toughness, and wear resistance. The exact composition of steel alloys is tailored for each application, balancing carbon content, alloying elements like chromium or nickel, and heat treatment processes to optimize properties. Carbon steels offer good hardness and strength, while alloy steels provide enhanced toughness and fatigue resistance. A key process in enhancing gear material properties is heat treatment. Techniques such as carburizing, nitriding, induction hardening, and flame hardening modify the surface layer of the gear teeth, creating a hard, wear-resistant exterior while preserving a tough, ductile core. This gradient of properties provides resistance to surface wear and pitting while imparting the ability to absorb shocks and stresses without fracturing. For example, carburizing involves infusing carbon into the surface of low-carbon steel gears at elevated temperatures, followed by quenching. The resulting surface layer becomes hard and wear-resistant, while the core remains more flexible to absorb stresses. Nitriding, in contrast, introduces nitrogen atoms to the surface, hardening without the need for quenching, resulting in minimal distortion and excellent fatigue resistance. In highly specialized applications, non-metallic materials or composites are sometimes used. For instance, plastic gears find their place in low-load, low-noise systems such as printers, office equipment, and toys. These materials reduce weight, cost, and noise, but lack the strength for heavy-duty applications. Advanced composites incorporating fibers and resins offer improved mechanical properties, sometimes competing with metals for niche tasks. Beyond gears themselves, the materials used in bearings, shafts, and housings integrate closely with gear materials to create harmonious systems. Thermal expansion compatibility, corrosion resistance, and lubrication chemistry all tie back to material choices. A gear made from high-strength steel, paired with incompatible components, can fail prematurely despite optimal tooth design. Corrosion resistance presents another critical challenge. In harsh environments, marine applications, chemical plants, or outdoor machinery, gears must resist oxidation and chemical attack. Special alloy steels, coatings, or surface treatments serve to protect against corrosion, preserving both functionality and lifespan. Material defects such as inclusions, voids, or microcracks can become the starting point for gear failures. Modern manufacturing employs rigorous quality controls, including ultrasonic inspection and metallurgical analysis, to detect and eliminate defective stock before machining begins. This assurance of material integrity is crucial in high-reliability sectors like aerospace or power generation. Material innovations continue to push gear technology forward. Powder metallurgy techniques enable the production of near-net-shaped gears with controlled porosity and customized properties, reducing machining costs and weight. Additive manufacturing, too, offers new possibilities for complex geometries and integrated functions, although challenges remain in matching the mechanical properties of traditionally forged metals. Sustainability considerations are also influencing gear material choices today. The energy cost of heat treatment, environmental impact of alloying elements, and recyclability shape how materials are selected and processed. Engineers are tasked not only with creating stronger, longer-lasting gears, but also with minimizing ecological footprints. The interaction between material science and gear design forms a rich tapestry where microscopic structures determine macroscopic performance. The grain size, hardness gradients, and surface chemistry all contribute silently, yet powerfully to how gears respond under millions of load cycles. When you witness a gear turning smoothly in your car or powering a piece of machinery, remember that beneath the surface lies a marvel of material engineering. Each tooth is a battleground where creations of chemistry and metallurgy stand strong against the forces of nature in use. Material science is the invisible backbone of gear reliability and innovation. As technology demands more from machines, materials evolve hand in hand, creating not only stronger and more durable gears, but enabling advancements in size, speed, and precision. This ongoing evolution in materials propels gear engineering to new heights, blending tradition, innovation, and sustainability. The story of gears is inseparable from the story of the metals, plastics, and composites that give them life, every revolution a testament to the science embedded within their surfaces. And so, as the dance of gear teeth continues, it does so bearing the strength of thousands of years of material development, a silent but steadfast contributor to the endless turning of machines and progress. The precision and effectiveness of gears depend not only on their materials and manufacturing, but also fundamentally on how engineers measure, classify, and maintain quality throughout their life cycle. The topic of gear quality and standards encapsulates a vast body of knowledge that assures gears manufactured anywhere in the world will perform reliably, interchangeably, and safely in their destined applications. Quality control begins with a clear understanding of gear accuracy grades, standardized by organizations such as the American Gear Manufacturers Association, AGMA, and the International Organization for Standardization ISO. These grades categorize gears based on permissible deviations in fundamental parameters, including tooth profile, pitch, runout, thickness, and surface finish. The classification system addresses both geometric accuracy and functional performance to assess durability, noise, vibration, and efficiency. At the lowest grades, gears are suitable for basic, low-load applications such as toys or household appliances, where precision and longevity demands are minimal. As the grade increases, tolerances tighten, producing gears fit for demanding environments. Automotive transmissions, aerospace mechanisms, and precision instruments. High-grade gears require meticulous machining and inspection, but reward with extended service life, reduced noise, and consistent performance under complex loads. Inspection methods involve a combination of traditional metrology tools and advanced modern technology. Precision instruments like calipers, micrometers, gear tooth verniers, and coordinate measuring machines provide measurements of physical dimensions with micron-level accuracy. Profile projectors and optical comparators allow visual examination of tooth shape relative to ideal curves. Laser scanning and digital imaging have revolutionized gear inspection, generating detailed 3D models for rapid comparison against design specifications. These non-contact methods not only enhance accuracy, but enable the detection of surface defects, micro cracks, or irregular wear patterns invisible to the naked eye. The data collected guides corrective actions, whether in manufacturing adjustments or maintenance scheduling. A vital part of quality assurance is the measurement of runout, the extent to which a gear's teeth deviate from their perfect circular path as the gear rotates. Excessive runout causes vibration, stress concentration, and uneven tooth loading, all detrimental to gear life and performance. Engineers use dial indicators or laser sensors to ensure runout remains within acceptable limits. Tooth thickness and backlash measurements also require high precision because they directly influence how smoothly gears mesh. Unbalanced backlash leads to noise and wear, while overly tight tooth engagements create binding and premature failure. Specialized tools such as gear tooth calipers and backlash analyzers characterize these details with great accuracy. Beyond dimensional accuracy, surface quality, and finish strongly influence gear efficiency and noise. Machine surfaces with minimal roughness promote better lubrication retention and reduce frictional losses. Gear grinders and polishers refine surfaces to mirror-like finishes where needed, contributing to quieter and more durable gear operation. Throughout the gear's operating life, continuous monitoring and maintenance are essential. Regular inspections detect early signs of wear, misalignment, or component fatigue. Condition-based maintenance, employing sensors that measure vibration, temperature, and acoustic emissions, allows predictive scheduling of repairs or replacements before failure occurs. This proactive approach increases reliability and reduces costly downtime in critical machinery. Gear design also incorporates safety factors derived from quality standards. Materials and manufacturing processes are selected and tested to withstand unexpected loads or harsh environments, ensuring gearbox integrity even under conditions harsher than normal operation. These considerations protect both equipment and human operators. As technologies evolve, so do the standards and practices governing gear quality. Innovations in additive manufacturing, new material composites, and intelligent sensor integration require adaptations in testing and inspection protocols. Standard bodies continually update classifications and guidelines to incorporate emerging technologies while preserving legacy interoperability. Ultimately, the pursuit of gear quality is a quest for perfection in motion, ensuring that every tooth meshes flawlessly, every rotation is smooth, and every system powered by these marvels fulfills its mission without compromise. In the grand orchestration of engineering, quality assurance acts as the vigilant conductor, maintaining harmony and rhythm amidst complexity. Thanks to these rigorous safeguards, gears reliably power industries, transportation, and technology worldwide. As you watch gears turning within any machinery, know that behind their steady motion lies an invisible world of measurement, testing, and refinement, a testimony to human commitment to excellence. It is this dedication that transforms raw components into trusted mechanical partners, silently sustaining progress and innovation turn after turn. Gears, despite their mechanical strength and precision, are subject to wear and eventual failure if not properly maintained. The science and practice of gear maintenance represent essential knowledge, bridging the gap between engineering design and real-world longevity. Understanding how and why gears fail and how to prevent it prolongs their useful life and preserves the safety and efficiency of the machines they power. The most common modes of gear failure include wear, pitting, scuffing, tooth breakage, and fatigue cracking. Each failure type originates from different causes: operating conditions, material properties, lubrication state, and manufacturing quality, requiring specific maintenance strategies and preventative measures. Wear is the gradual removal of material from gear tooth surfaces, caused by frictional contact and sliding during gear engagement. Over time, wear alters tooth profiles, increasing backlash and noise, reducing efficiency, and eventually affecting load-bearing capacity. Minimizing wear depends largely on effective lubrication that forms a protective film between teeth, reducing direct metal contact. Monitoring lubricant condition is critical. Contaminated, degraded, or insufficient lubrication accelerates wear dramatically. Pitting refers to small surface cavities or pits that appear on the hardened gear tooth surface, caused by subsurface fatigue stresses. These microcracks initiate at points of maximum pressure and grow until small chunks break away. Pitting weakens teeth, leading to rough operation, noise, and potential failure. To prevent pitting, gears must operate with proper load distribution, maintain correct alignment, and use appropriate materials and heat treatments. In harsh conditions, scuffing or surface welding can occur, where insufficient lubrication combined with high load and temperature causes local metal adhesion. This leads to severe surface damage and rapid gear failure. Preventing scuffing involves maintaining lubricant film integrity, controlling operating temperatures, and applying correct surface treatments. Tooth breakage is a catastrophic failure mode caused by excessive load, high impact forces, or existing cracks worsening over time. Breakage can result in sudden machine shutdowns and extensive damage. Proper gear selection, correct installation, careful alignment, and avoiding shock loads are crucial to preventing tooth fracture. Fatigue cracking develops slowly through repeated stress cycles, causing microscopic cracks in tooth roots or surfaces. Over time, these cracks propagate, eventually leading to tooth failure. Regular inspection and non-destructive testing, such as magnetic particle inspection or dye penetrant testing, help detect early fatigue and enable timely repairs or replacements. Gear maintenance practices emphasize lubrication management. Selecting the right lubricant with proper viscosity, additives, and thermal stability is fundamental. Lubricants must be regularly monitored and replaced to avoid contamination with dirt, metal particles, or water, which degrade lubrication performance. Advanced systems implement oil filtration and circulation to maintain clean, cool lubricant environments. Routine cleaning and inspection are vital to identify early signs of wear, cracks, or corrosion. Visual inspections, combined with vibration and acoustic analysis, provide comprehensive monitoring. Vibration analysis detects abnormal frequencies indicating gear defects before visible damage occurs, while oil analysis assesses metal wear particles in lubricant, signaling deteriorating conditions. Proper alignment and adjustment prolong gear life. Over time, mechanical stress, thermal expansion, or foundation settling may cause shafts to shift, increasing misalignment. Since even minute misalignment affects load distribution and accelerates wear, periodic adjustment and shaft positioning using dial indicators or laser alignment tools are part of preventive maintenance. Repairs range from minor surface treatments and regrinding of worn teeth to complete gear replacement in severe cases. In some situations, surface coatings or overlays can restore gear functionality temporarily, reducing downtime. Engineers and maintenance professionals must establish comprehensive maintenance schedules based on operating conditions, load cycles, and manufacturer recommendations. These schedules balance maintenance costs with the risk of unplanned failures, optimizing machinery uptime and reliability. The move toward predictive maintenance, enabled by sensors and real-time data monitoring, is transforming gear maintenance. Condition monitoring allows early detection of anomalies, supporting preventative action before catastrophic failure. With advances in machine learning, systems predict remaining useful life and recommend timely interventions, enhancing safety, efficiency, and cost-effectiveness. Proper training and adherence to standards further ensure maintenance effectiveness. Knowledge of gear mechanics, lubrication science, and inspection techniques equips technicians to address complex gear system needs. In essence, gear maintenance is a continuous dialogue between man, machine, and material. It ensures that these mechanical components, which quietly endure millions of revolutions daily, remain reliable partners in the machines shaping our world. Through diligent care, gears transcend their physical limits, forging long-lasting service and safe operation. In their silent persistence, these spinning teeth drive not only machines, but the confidence of engineers and operators alike. As the world turns, so do gears kept in motion by science, vigilance, and the timeless commitment to mechanical excellence. Gears are much more than simple mechanical components. They are central to the art and science of innovative gear technology, a dynamic field constantly evolving to meet new challenges and unlock fresh possibilities. The quest for higher efficiency, lighter weight, quieter operation, and longer life fuels groundbreaking developments, pushing gear systems beyond traditional limits. One major frontier in gear innovation is advanced materials. Researchers and engineers experiment with novel alloys, composites, and surface coatings designed to enhance strength and reduce friction. Lightweight materials such as titanium alloys and carbon fiber composites are being integrated into gears for aerospace and automotive applications to save weight without sacrificing performance. Nanostructured coatings and diamond-like carbon films dramatically improve wear resistance and reduce energy losses due to friction. These advances increase gear durability and efficiency, playing a critical role in sustainability by reducing energy consumption and extending service intervals. The application of additive manufacturing, or 3D printing, offers profound possibilities. Unlike conventional subtractive machining, additive techniques build gears layer by layer, enabling intricate geometries impossible to produce before. This freedom allows designers to create optimized internal structures that reduce weight and incorporate cooling channels or integrated sensors within gear bodies. Rapid prototyping accelerates development cycles, while low-volume, custom gear production becomes more accessible. Although challenges remain, such as achieving material properties matching forged gears, ongoing research continues to close the gap. Another cutting-edge area involves smart gears, integrating sensing and communication technologies directly into gear systems. Embedded sensors monitor temperature, vibration, strain, and lubrication conditions in real time, feeding data into predictive maintenance platforms powered by artificial intelligence. These smart systems detect early signs of wear or misalignment, enabling actionable insights and avoiding costly downtime. The converging fields of the industrial Internet of Things, IoT, and gear technology promise a future where gears not only turn, but also think. In pursuit of quieter machinery, noise reduction technologies are a major focus. Advanced gear tooth designs, including asymmetric profiles and optimized flank modifications, decrease vibration and tonal noise. Novel lubrication strategies such as micro-textured surfaces retaining lubricant films and damping materials integrated into gear housings further suppress noise. These improvements enhance comfort and meet stringent regulatory noise limits across industries from electric vehicles to consumer appliances. Increasingly, computational tools revolutionize gear design and analysis. Engineers use powerful simulations incorporating finite element analysis, multi-body dynamics, and tribology modeling to optimize every aspect of gear systems before physical prototyping. Topology optimization algorithms seek lightweight yet strong structures, helping design gears that use less material without compromising performance. Virtual testing enables rapid exploration of design variations, shortening development timelines and costs. Hybrid gear concepts also emerge, combining benefits of multiple gear types. For example, combining harmonic drive technology with planetary gear trains yields compact assemblies offering ultra-high gear ratios with minimal backlash, ideal for precision robotics and aerospace actuators. These hybrid solutions extend application horizons beyond conventional limits. Sustainability drives innovation as well. Eco-friendly manufacturing processes reduce waste, and recyclability of gear materials gains emphasis. Energy-efficient gearboxes lower operational carbon footprints, contributing to greener industries. Finally, the human element remains central. Advances in education, digital twins, and collaborative design platforms connect gear experts worldwide, allowing shared knowledge, testing protocols, and innovations to flourish. This collective brainpower accelerates progress beyond isolated effort. Through these innovations, Gears continue to embody human ingenuity and progress. They evolve from simple rotating wheels with teeth into sophisticated components embedded with intelligence, optimized for unprecedented performance and sustainability. The gears of tomorrow promise to be lighter, smarter, and more durable, quietly powering industries, transportation, and technologies yet to be imagined. As the journey through gear technology unfolds, it becomes clear that these mechanical marvels are not relics of the past, but vibrant foundations of future engineering wonders. The eternal dance of teeth engaging, turning, and transforming energy persists, forever advancing with creativity and science. The story of gears is far from finished. It is alive, breathing innovation and evolving endlessly with the turn of every wheel. And so the gears keep spinning, carrying the promise of tomorrow on their steady, unceasing path. As we draw this extensive exploration of gears to a close, it is fitting to reflect on the broader significance of these remarkable mechanical components, whose influence extends far beyond their physical form. Gears symbolize a fundamental human achievement, the transformation of abstract concepts, force, motion, precision, into tangible, reliable technology that shapes our civilization. From the simplest wooden wheels carved by ancient hands to the intricately engineered computer-designed gear systems of today, these components have been silent catalysts of progress. They represent the marriage of innovation and tradition, where centuries of accumulated knowledge enable us to build machines of incredible complexity and capability. Throughout this journey, we witnessed gears as both humble and heroic, simple in appearance, yet vital in function. Their teeth, designed with mathematical precision, interlock flawlessly to transmit power, control speed, and change direction, fueling the machinery of daily life, from timekeeping to transportation, manufacturing to exploration. We explored how gears are crafted, inspected, and maintained with painstaking dedication to ensure longevity and dependability. We revealed the hidden stresses at play within each tooth, the intricacies of material science defending against wear and failure, and the vital role of lubrication and alignment in sustaining smooth operation. We saw how standards and quality control elevate gear performance, enabling interoperability and global innovation. More than that, we delved into the awe-inspiring diversity of gear technology and applications. How these spinning wheels with teeth shape modern industries, from the mass movements of vehicles and energy systems to the subtle maneuvering of robots and instruments. They are everywhere, often unseen, yet indispensable. Looking forward, the future of gears gleams brightly with promise. Advances in materials, manufacturing, smart sensing, and design algorithms ensure that gears will continue adapting to new demands, becoming lighter, stronger, quieter, and more intelligent. Gears will not only power machines but also communicate their condition, anticipate their needs, and optimize their operation, integrating seamlessly into the fabric of digital, sustainable industries. This endless evolution mirrors the human spirit that created them, the desire to understand, to innovate, and to improve. Gears are emblematic of engineering as a whole, a field where curiosity meets precision, creativity meets discipline, and knowledge meets application. So as you pause to consider a gear turning inside a machine, remember it is more than metal and mechanics. It is a triumph of science and imagination, a legacy of countless engineers, and a promise of future marvels yet to come.